Today we start countable and uncountable set. In previous class we also discussed about finite sets and consequent theorem lemmas and corollaries. That means some properties of finite set and how we understand which one is finite set. Okay, by these properties or all properties of finite set we discuss here, and which set is finite or not also discussed in previous class. So today we discuss countable or uncountable set. Okay, one important topics in set theory: countable and uncountable set. Which one we call finite? A set A is called finite when cardinality of A is less than plus infinity. Now one set A set, then this implies A finite. Okay, and obviously some properties are here, but now we discuss about countable sets. So we tell about a set is said to be infinite. A set is said to be infinite if it is not finite. If it is not finite. Okay, so simple rule: it is not finite, then infinite. It is countably infinite, and also it is said to be countably infinite. Then there exists a bijective correspondence. If there is a bijective correspondence if A to Z plus, okay, that means a set A is said to be infinite if it is not finite, and it is said to be countably infinite if there exists a bijective correspondence with Z plus. Okay, now we give some example of countable or countably infinite set. Examples: first one, we discuss about the set Z of all integers is countably infinite. Set Z of is countably infinite. Okay, that means infinite set, but this one is countable. Then there exists a bijective correspondence with this set and Z plus. How we define it? We define it in this way: if Z to Z plus such that f of n equal to 2n when n greater than 0 and minus 2n plus 1 when n less than equal to 0. Okay, that means this one is so simple. If n equal to 0, then this one is 1, n equal to 1 2, and n equal to minus 1, then 3. So this one is trivially f Z to Z plus is a bijective correspondence. That means this f is a bijection. Okay, then we know about that this Z is countably infinite. Now we give second example which clear this definition. Okay, how we construct this example: this one is Z plus Cartesian product of Z plus is countably infinite. Okay, Z plus Cartesian product of Z plus is countably infinite. Then Z plus and Z plus cross Cartesian product of Z plus is obviously one bijective correspondence with some set. Then we represent the elements of the product by the integer points in the first quadrant. Then left hand portion of some figure, we draw this figure here. Okay, here A1, here A2, A4, A3 here, A5 here, in this way. Okay, and a6 a7 in this way. This f going to these two f going to here, this in this way. Okay, that means how this one is possible. This one is possible if we define a bijection f. If we define a bijection f from, we erase these things, that portion. So now we're done or proceed further. Then we define a bijection f z plus Cartesian product of z plus 2a. How? Where a is subset of z plus Cartesian product of z plus, and corresponding xy such that y less than equal to x. That means this pair xy such that y less than equal to x, and here fxy equal to x plus y minus 1, here y. Okay, then we construct a bijection a with the positive integers. Okay, then we construct a bijection, that means defining g a to z plus. How this one is defined? Gxy equal to half x minus 1 x plus y. Okay, then f and g are both are bijection. F and g both are bijection. So we going to the conclusion, z plus Cartesian product z plus is countably infinite. Then we construct in this way. That means first we define z plus cross Cartesian product z plus to a, then a subset of z plus Cartesian product z plus, and define in this way. And then fxy equal to x plus y minus 1 y, and g a to z plus, such that this one defined such that gxy equal to half x minus 1 multiplied by x plus y. Okay, then f and g both are bijection, and z plus cross z plus is countably infinite. So we're going to further one, a set is countable or not. That means we erase these things. Here if we discuss about that f and g are bijection or not, then this one is better, but not, I am not interested about that now. Okay, so we're going to further. Then give some definition of countable set and uncountable set. A set is said to be countable. A set is said to be countable if it is either finite or countably infinite. If it is either finite or countably infinite. Okay. Countably infinite means a bijective correspondence with Z plus, and finite means they are cardinality less than plus infinity. So in this way we call this set is countable. Okay. Then next, a set that is not countable is called uncountable. A set that is not countable is called uncountable. Now we discuss some theorem. Okay, we discuss some theorem about that. Let B be a non-empty set. Let B be a non-empty set. Then the following are equivalent. Then the following are equivalent. B is countable. There is a surjective function f z plus to b, and number 3, there is an injective function a b to z plus. Okay, then we're going to this proof of this theorem. Okay, b is countable, that means 1 implies 2. Countable implies there is a surjective function from z plus to b. Suppose b is countable. Suppose that b is countable. Then if b is countably infinite, if b is countably infinite, then there exists a bijection f z plus to b. And also if b is finite, if b is finite, if b is finite, there is a bijection h 1 to dot 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 n to b for some n greater than equal to 1, and b not equal to 5 also. Then we can extend h to a surjection. We can extend h to a surjection f z plus to b by defining fi equal to hi for 1 less than equal to I less than equal to n, and h1 for I greater than n. Okay. Then if B is finite, there exists a bijection, and also this bijection extend to fz plus to B. And if B is countably infinite, then there exists a bijection fz plus to B. Then we're going to this conclusion. There is a surjective functions if z plus 2b. Okay. Now we proceed further. So we erase that whole portion. Next we're going to further. So okay. So now we're going to further 2 implies 3. If let f z plus to be a surjection, then define b to z plus by the equation define g b to z plus by the equation gb equal to smallest element of f inverse b, because f is surjective. Because f is surjective, f inverse b is non-empty. Then g is well defined. The map G is injective for if B not equal to B dashed. The set F inverse B. The sets F inverse B and F inverse B dashed are disjoint. So their smallest element are different. Now if Z plus to be surjection, then if G B to Z plus by the equation the smallest element of F inverse B. F is surjective, then F inverse B is non-empty. Then G is well defined. The map FG is injective. For if B not equal to B dash, the set F inverse B and F inverse B dash are disjoint. So thus their smallest element different. Then we get a G map G. We get a map G which B to Z class is injective. Okay, then we're going to further proof of 3 implies 1. Next, let G B to Z plus be an injection. We wish to prove that B is countable. We wish to prove that B is countable. By changing the range of G, we can obtain a bijection of B with a subset of Z class. Okay. Then this one is an injection. That means by changing the range of G, by changing range of G, we obtain a bijection. We obtain a bijection of B with a subset of Z class, of B with a subset of Z class. Okay, then we have to now thus we have to suffices to show that every subset of Z class is countable. If every subset of Z class is countable, then B is countable because there is a bijection. Okay, then so let C be a subset. So now we have to prove our result. If we have to prove our result, then to show that a subset of Z class be countable. So now taken C be a subset of Z class. Then now if C is finite, then countable, then it is countable. Okay, now every infinite subset C of Z plus is countably infinite. Then we need to prove that every subset C of Z plus is countably infinite. So what we do, for elements of C can easily arranged in an infinite sequence. For elements of C easily arranged in an infinite sequence. Okay, so Z plus in an usual order and erases all elements of Z plus that are not C. Then we going to conclusion that every infinite subset C of Z plus is countably infinite. Okay, that means here for elements of C easily arranged in an infinite sequence. Now we going to simply takes the set Z plus in usual order, take Z plus in its usual order, then erase all these elements, erase all the elements of Z plus that are not in C. Then we going to also a infinite sequence that is countably infinite. Then we going to conclusion also C is an infinite subset of Z plus that is countably infinite, and we prove it. Also we have to prove that. So what we do if we define a bijection Az plus to C. Okay, then we proceed by induction. We proceed by induction. Define H1 is the smallest element of C. Define H1 be the smallest element of C. Then define H1 be the smallest element of C. It exists because every non-empty subset C of Z plus has a smallest element. It exists because every non-empty subset C of Z plus, every C of Z plus has a smallest element. Okay, then assuming that are defined and define Hn equal to smallest element of this, then the set is not empty. Okay, then the set is not empty. For it were empty, for it were empty, then H to C would be surjective. So that C, then assuming that h1 h2 hn minus r1 are defined and hn are smallest element of this, then the set C difference h of 1 to dot 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 n minus 1 is not empty. For if it were empty, then h 1 to dot 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 n minus 1 to C would be surjective. So that C. Okay. So that C would be finite. So that so we completely then thus hn is well defined. By induction we have defined hn for all n belongs to Z class. To show H is injective, given m less than n, note that Hm belongs to the set this one. To show H is injective, H less than m, then Hm belongs to the set H1 2 dot 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 n minus 1. Now, whereas Hn by definition does not. Whereas Hn does not. Hence Hn not equal to Hn. Okay. Then we should to show H is surjective. She lies in the image set of H. First note that Hz plus cannot be contained in the finite set. Because Hz plus is infinite. Now therefore there is an n in Z plus such that Hn greater than C. Let M be the smallest element of Z plus such that Hm greater than equal to C. Okay. Now then for all I less than M, we must have Hi less than C. Thus C does not belong to the set this. Since Hm is defined smallest element of these, we must have HM less than equal to C. So we're going to this conclusion that HM less than equal to C and HM greater than equal to C, then HM equal to C. So H is surjective. Okay. Then we prove that C is an infinite subset of Z plus, then C is countably infinite. So today stopped here.